Hello everyone. Let's continue our discussion. So we were at a point where we have built the clock tree, and the clock tree was built in such a fashion that it maintained zero skew between the launch flop and the capture flop. For example, if this was the launch flop and if this was the capture flop, we made sure that the clock tree that we have built maintain a zero skew. By skew we mean the latency difference between the clock port to this particular flip-flop clock pin minus the clock port with this particular flip-flop clock pin. Okay, that's basically the latency, the difference, that's basically the skew, the difference in the latency of this clock and this clock. And we have talked a lot about latency, skew, and all those things in the CTS videos. In the CTS videos that has been uploaded on Udemy, you might want to have a look into those videos. So next is the clock net shielding. So clock nets are considered to be the critical nets in your design because we have built the clock tree in such a fashion that we have zero skew. But accidentally, if there is something, if there is a phenomena, there is a phenomena of crosstalk that can happen. If that phenomena occurs on these lines, your everything, whatever you have designed in the clock side, that might get deteriorated. And how we have a complete course on crosstalk that has been uploaded on Udemy. You might want to have a look into those videos. But before that, let me give you a brief discussion on clock net shielding. So what we do is we take all the clock nets. For example, let's say we will take an example of this particular clock net. We take this particular clock net and shield it, something like this. By shielding, what we do, we protect this clock nets from the outside world. It's like we are encapsulating this clock nets to be protected from the outside world. It's like a house for the clock net. Okay, so any signal which is lying, let's say any signal which any net which is lying over here, any wire which is lying over here, there will be some activities happening on that particular wire. And that activities, if the coupling capacitance between that wire and this particular net is very huge, then there might be some coupling happening between the wire which is sitting over here and this clock net. And as a result of that, there are a couple of problems. There are two problems basically. One is glitch and one is delta delay. Okay, so we have talked about glitch and delta delay in complete detail in the crosstalk videos. So let me give a brief description on that. So what happens if there is a glitch? First of all, what is a glitch? So just for example, consider this as one of the clock nets, though it shows the reset pin. Let us consider this is one of the clock nets or one of the nets, and this is the aggressor. So whenever there is a switching activity happening on the aggressor, because of the coupling capacitance, and the coupling capacitance is so strong that any activity happening over here will directly impact the net which is sitting close to it. And this is the net we are talking about without shielding. This is a clock net without shielding. What can go wrong? Okay, and as a result of that, you see there is a glitch over here. So this victim was supposed to be at logic 1, but because of this particular aggressor getting from logic 1 to logic 0, you see there is a dip in the voltage, and as a result of that you see a glitch. And what can go wrong if you see this kind of glitch? So for example, if this was your memory and memory was initiated with numbers like whatever you see over here, this was supposed to be the memory contents. Accidentally, because of this particular glitch getting inverted by with this particular inverter, you might receive a logic high at the reset pin, and your complete memory might get reset. And this memory could be a part of any automobile chip or any of the critical chip. And if that thing if it's a part of a critical chip, then if and this thing goes wrong, then the complete system goes wrong. So that's why the glitch has become increasingly important factor to be considered while doing a clock tree building, or while doing basically while doing a VLSI design, while doing physical design, while routing. This particular phenomena has become an increasing point of concern for all the VLSI engineers, and all of them are working towards it. So shielding is one of the technique that will actually protect this particular victim. So shielding basically says that we put a line over here, we put a wire over here, and these wires are connected either to VDD or ground, because VDD and ground are the ones which won't switch. And as a result of that, your victim is protected. So we have talked about all of them, all of this phenomena in the crosstalk videos, which has been uploaded on Udemy. You might want to have a look into those videos. So yes, this is the technique. We shield it. We basically, by shielding, we are breaking the coupling capacitance between the aggressor and the victim. Okay, so shields are either connected to both we place a wire over here, we place a wire over here, and either both the shields are connected to VDD, or they're connected to ground, or one is connected to VDD, one is connected to ground. The idea is the shields don't switch, and if the shields don't switch, there is very less possibility that the victim will switch. There are other problems where there are ground bounce and voltage drop, so we have talked about all those in the crosstalk videos. Okay, and there is one more thing that can happen. This is we talked about glitch, but what happens if there is if the victim itself was switching and the aggressor is also switching, then what can go wrong? So let's say this was the clock tree that we have built. We have just taken the clock tree from the above circuit and placed it in an ideal way. So for example, this is the clock port. Okay, this is one of the flops, and this is there is one flop over here, and there is one flop over here, and we have built the clock tree in such a fashion that we maintain a zero skew. So by zero skew we mean that, let's say, the latency of this particular latency from this clock port to this point of the flop is L1. Okay, and let's say the latency from this clock port to this flop, which is sitting over here, it is not shown but it is sitting over here, is L2 before crosstalk, if it was L2. So we built this clock tree in such a fashion that L1 is equal to L2. Okay, but now what happens because of crosstalk? If you see, there is some amount of delta delay, there is some amount of glitch. So for example, this is the line, victim line. The input of the victim line is switching from logic 0 to logic 1. So output of the inverter will be logic 1 to logic 0. It is supposed to go from logic 1 to logic 0. Okay, but what can go wrong because of this particular glitch that you see? It might impact the logic 1 to logic 0 direction by some amount of delta delay. Okay, if you see this particular thing, there is it was going from logic 1 to logic 0, but on its path it sees it sees the aggressor moving from logic 0 to logic 1. As a result of that, this particular thing tries to charge and then again gets discharged, and because of this amount of bump, you see an amount of delay, you see an amount of delta delay while switching from logic 1 to logic 0. And as a result of that, the delay of this particular cell gets impacted. So initially, if the delay of this particular cell is D, after the crosstalk delta delay, you see the delay of this particular cell is D plus delta. And let's say if this clock cell was a part of L2, if this clock cell was part of L2, this particular cell delay, which was supposed to be D, now it is D plus delta. Your complete L2, your complete latency, which was supposed to be L2, is now L2 plus delta. So now your skew becomes L1 minus L2 plus delta. So it's no more 0, there is some finite value delta. And imagine we have talked about only, let's say, few buffers, handful of buffers. It's like 5 to 6 buffers. If the clock tree was for a multi-million chip, this delta might grow very exponentially or linearly. Okay, so that's the impact of crosstalk, and we are trying to protect our clock nets from crosstalk by putting a shield around the clock nets. So shielding is one of the technique to protect the nets from crosstalk. There are other techniques as well. We have talked about them in the crosstalk videos. You might want to have a look into those videos. These slides are being taken from there, and there are a lot more slides which talks on the similar lines. Okay, so that's the idea of that's the idea of crosstalk, and this is the reason we shield the clock nets. Ideally we are supposed to shield this one also, but we have just left it that way. So this net will also get shielded, something like this. So the idea is we have to shield all the critical nets. Clock nets is one of the critical nets, and let's say if there are some data nets which are also supposed to be critical, we'll be drawing the data nets in the next video. But if there are data nets which are very critical, it becomes necessary to shield them. But it's not always possible to shield all of the nets in the design, because that might just increase the routing resources over here. As a result of that, we take the clock nets, we take the critical nets and shield them, and clock nets are one of them. Okay, so after we have done with the clock net shielding, the next step is to do again a timing analysis with real clocks, because now we have the clock nets and now we have the clock net shielded. So this is the point where we have to do a timing with real clocks. Though the data paths are not routed, we'll be doing a timing analysis with real clocks, and that's the part of the flow. That's the part of an ideal flow. Okay, so what we'll do is we'll talk about this particular slide in the next video, since I'm already running out of time. So let's continue understanding about this particular equation and how does the clock delay looks like in the next video. Thank you.